Guys can please turn on. All right. Today is the third day of the Paragon X techniques, advanced techniques and mechanics class. We're gonna be talking about oscillations and rotations. But first, we're gonna go over the homework. Yeah, we're gonna go over homework and then we'll start the lecture and you guys can do some cool problems about oscillations and simple rotation problems. That's what we're gonna focus on today. The homework review, right? This time I won't be going over every homework problem because last class we spent a bit too much time on the homework and then we didn't have much time for the lesson. So I'm gonna try to only go over like the most important homework problems and just give a general overview on how to solve the problem. So in case you were stuck or like didn't attempt the problem yet, you guys can get a chance to still do that, right? Well, even though you'll still get the idea of how to do the problem. So let's look at the first problem. An object is launched from the top of a hill where the ground lies at an angle phi below the horizontal. Show that the range of a projectile is maximized if it is launched along the angle bisector of the vertical and the ground. All right, so I'll go over the general idea of how to solve this problem. So let's just draw a picture first, right? So I'll say my hill looks something like a ramp, because we're just saying the hill is like it's just sloped at a constant angle with the horizontal. And then hold on, let me draw that a bit lower. Okay, so our hill will be over here, and then we're launching a projectile from the top, right? And then we want to maximize the range of the projectile. So the projectile will be launched over here and it'll land somewhere there, right? So that will be the motion of the projectile. Now, we want to maximize this range. And what's tricky about this problem is that our hill, right? It's a hill, it's not like flat ground, it's sloped with respect to the horizontal. So if the hill, this angle over here was zero, then it would just be flat ground, right? If it's flat ground, then of course you guys should know that the range of the projectile will be maximized if it's launched at a 45-degree angle, right? So it will go over there. This should be 45-degree angle. And indeed, that is true that it's launched between the vertical, so that direction and this direction. It's at the angle bisector. Now, if you want to prove that for this case where we have like a sloped hill, right? Saying it's launched along the angle bisector between like that direction and the ground direction. So those two angles should be equal, right? Um, those are two equal angles. Well, a convenient way to do this would be if we rotated the hill or sort of rotated our point of view so that the hill, instead of looking like it's sloped, it's actually horizontal. What do I mean by that? You guys might be wondering. Well, instead of looking at this, I'll look at, let me change the color for you guys. Okay, so we have the ground over here, and now, like, I'm looking at the hill instead of being sloped, it's like flat, right? But the problem with that is that we need to change the direction of the gravitational field, right? Because in this case over here, my gravitational field was pointing this way, right? It has field strength G, right? If I rotate my frame of view so that it looks like uh the hill is horizontal, like if you tilt your head a bit, you'll see that G it now points in this direction, right? This is the new direction of G, or I'll say G star, right? And then uh I have like vertical component and horizontal component of G, right? Now, okay, so I want to maximize the range, right? If you want to solve this problem, like you can definitely bash it out. So a more intuitive answer to this problem would be to say like, look, uh I want to launch this an angle, for example, like this is the direction of the gravitational field, right? It's going this way, and my ground is in the horizontal, right? So I can sort of draw an analogy to when we were launching the projectile over here. And if I launch it at this angle bisector, what does this do? Well, notice that because because the component of the gravitational field is pointing to the right, right? So it will be accelerating the projectile towards the right, right? That increases the range. What does that mean? That means that we can afford to have more vertical initial velocity, right? Because even though you'll have a smaller horizontal initial velocity, you still have a component of the gravitational field that points towards the right, and that allows you to accelerate from a smaller initial x velocity to a eventually it will be a much bigger it'll be a larger x velocity, right? So if I launch it at an angle over here, it intuitively makes sense that we'd be able to maximize the range. Of course, if you really want to answer this problem with rigor, I would recommend you to just like write out the kinematic equations and just bash it out. But this is the more intuitive answer that's like it helps you understand the physical process. So we're not gonna like write out all those messy equations and eventually solve it. I'll leave that to you. You also don't have to do it just as long as you understand the reasoning why uh we want to launch the projectile at an angle that's greater than 45 degrees. Okay. Uh yeah. So that's the first problem. Let's go on to the second problem, which should hopefully make a bit more sense to you. Yeah, this is just a pulley problem. Find the accelerations of both masses. Well, remember for pulley problems, right? There are two main things you have to do. First thing is you have to write the F equals ma equations for for every mass that's in the system, right? So first write your F equals ma. This is first step, right? Second step is to write conservation of string. So conservation, say cons string. What does conservation of string mean? Well, it means that like basically because we have a fixed amount of string in the system, right? Like there is no like sort of reservoir of string or like rope, right? Because those points over there, they're fixed. They can't move upwards or downwards. So we have a fixed amount of string in our system. And because of that, we're able to relate the accelerations of like all the masses in our system. So over here, we just have two masses, so it's a bit silly. So first, let's write our F equals ma equations. But before that, we need to like write or draw a free body diagram, right? So on the bottom mass, let's say there's a downward gravitational force, right? Of course, and then there's an upward tension force. So let's call that T. Yeah, let's just call that T bottom, right? T bottom, and then this will be mg, except we also have a T top here, right? Okay, and then all right, we want to first relate TB and TT, right? Because like we have a system of pulleys and it's not too hard to relate the tensions of the ropes at different parts of the pulley. So how do we do that? Well, okay, if I look at this wheel over here, so I'll draw another picture over here. That's the bottom wheel. There's a string going this way, and it's connected to this wheel over here, right? There's a string connected there and so on, right? So I'm saying we have a mass here and it's being pulled up by tension force TB. Well, if there's a tension TB in that string, then that means that the string is pulling down on that pulley wheel, means yellow, okay. It's pulling down on that pulley wheel with the force of TB, right? Because the tension in the string is uniform because because the string doesn't have any mass, right? Now, how do I use this fact to find the tension in like this string over here? Well, notice that if we box this system over here, like basically the pulley wheel, that pulley wheel, it's also being pulled up by those two tension forces. And those two tension forces, they're the same tension force because it makes up the same It's like it's the same string, right? So that means that twice of the tension force in this string should be equal to TB. So if I draw that on our big diagram, let me erase this so that we can get a bit more space later. So on our big diagram over here, oh, then this, oh, yeah, this string over here, it has tension of, oh shoot, my bad. We have, so 2 times, let's say, tension 1, that should equal to TB. Then that means the tension on this string should be TB over 2. So that has tension T equals TB over 2. Now, notice that it's the same thing if I want to find the tension in this string, because this pulley wheel over here is being pulled up by 2 tension forces due to that rope over there, but it's also being pulled down by a tension force of TB over 2. So if I balance my forces on the pulley wheel, oh, then the tension on this one over there, that has tension T equals TB over 4. And if I do the same thing, now this one, it would have tension T top equals to TB over 8. So then I can write my F equals ma equation. So M, say A top, that equals to, that should equal to, if I let my top direction will be positive, so I'll get TT minus MG. And then my other equation for the bottom mass will be M A bottom equals to T bottom minus MG. Bottom minus MG. And now our final task is to relate AT and AB because we have 2 unknowns, right? We have TT and TB, or well, actually, yeah, we have 2 unknowns, which is just AT and AB. We already, yeah, we basically have 3 unknowns actually. We have AT, AB, and then we already related TT and TB, right? So TB is just 8TT, so I can replace this over here. That would just be 8TT, right? And then, yeah, now I want to relate AT and AB. Well, notice that if I'm looking at this mass over here, right? If this mass over, like the top mass, it travels up by a small amount, then this pulley wheel, it would travel down by half of that amount. Why do I say half? Well, it's because if I have this wheel over here, yeah, I have this wheel over here. If I add like a small a length of string to this side, then the result, for example, let's say this is DL, right? Then the result will be that the pulley wheel, it goes down by DL over 2 because there are 2 sides of, like, the string is on 2 sides of the pulley wheel. So if one side goes down by DL, the other side, like, it has to balance out on both sides. So it'll go down by DL over 2 on the left side, it'll go down by DL over 2 on the right side. So in total, the center of mass, it goes down by DL over 2, okay? So what does that mean? That means the acceleration of pulley wheel, this pulley wheel has acceleration of a top over 2, except it's negative. Oh, sorry. It's negative, right? Oh my God. Hold up. Yeah. How about I draw that? This one should have acceleration of negative a top over 2. Why do I say negative? The reason why it's negative is because when this mass moves upwards, the pulley wheel will move downwards, right? So the accelerations, they should be negatives. Now, again, if this pulley wheel moves down or it has an acceleration of negative AT over 2, then this one would have an acceleration of negative AT over 4. Because again, there's strings going on both sides of the pulley wheel, so you expect the acceleration to be half of the acceleration of the other pulley wheel, which is half of the acceleration of the mass. If I do the same thing, then what do I get? I get that this over here, which is the acceleration, it's the bottom pulley, right? So I'll get AB is equal to negative AT over 8. Now, when I plug that back into my equation, right? Uh, AB negative AT over 8. Yeah, so I'll get me erase this one over here. Then I should get negative AT over 8. By the way, you have to be careful about your positive or negative signs. It's very easy to mess this problem up if you don't get your signs correct. So yeah, and then now it's just a matter of algebra. I think you guys can do it now. Yeah, because you have two unknowns, right? You have AT and TT, and then you solve for both of them. Oh, so the final task of this problem, solve these two equations and you'll get your final answer for AT. And then once you know AT, you'll know AB, which equals to negative AT over 8, right? This should be AT. And then yeah, that'll just be your final answer. So now it's just all algebra, but just remember when you're solving these pulley problems, write your F equals ma equation, relate some forces together, for example, the top tension force, the bottom tension force, and then after that, write your conservation of string equation. Does that make sense, everyone? Any questions about that? I guess not. So let's keep going. Right, yeah. So we can skip this one because this was basically in last week's slides, last week's class, but the overall idea is you want to have momentum conservation, make sure that uh you just want there to have like you can't have any external net force on the system. Internal forces don't matter because they'll always cancel out. But remember, if you have momentum conservation, like you need dp equals f dt equal to 0, right? That's for momentum conservation. For energy conservation, remember we defined what potential energy was. Um, as long as you have only conservative forces, then you can define a potential energy, which means you can have energy conservation. So that basically answers both parts B and C. Yeah, that's just should be conceptual and it's a good mindset you should have when you're solving like physics problems, for example, in thermodynamics. Doesn't have to be mechanics, right? Let's keep going. Prove that in the center of mass frame of a system of mass points, the total linear momentum of these mass points is 0. This will be just a bit of algebra. So, for example, if I have two masses, m, and it travels at a speed, let's say u, just not confuse it with another one. So for example, if I have big M, which now travels at velocity v, right? Then what's the center of mass velocity? Well, I'll get VCM equals to mu plus mv over m plus n, right? Meaning that in the center of mass frame, U star, which I'll say is just the velocity of the small mass, or like velocity of small m in the center of mass frame. That would just be equal to U minus VCM, right? U minus VCM. That equals to, let's see, that once we do the algebra, so U minus MU plus MV over M plus M. So we do that, that should equal to I believe times m times u minus v over m plus n. And then we get v star. V star, it equals to v minus vcm. We do the algebra, that should equal to, well, I'm trying to do in my head right now. So it should be m small m times v minus u divided by m plus n. Now, if I want the momentums of both of the two, I'll multiply by each particle's mass, right? So that means that so P m star, right? That equals to m small m big M u minus v over m plus m. And notice that if I do the same thing for this big mass, right? If I multiply m over here, that's exactly equal to negative p of the big mass in the center mass frame. So that means that if I do sigma p in the center mass frame, it equals to 0. And you'll find, for a general system with like any arbitrary number of mass points, it doesn't have to be 2 mass points, we'll get that the total linear momentum is equal to 0. It doesn't have to be just for 2 mass points. So this is really convenient because a lot of times when you're solving collision problems, it's pretty easy to go in the center of mass frame so that you can just say that the momentum, well, okay, if momentum's conserved, right? You can say that the momentum before the collision should equal to the momentum after the collision. And it's an uh yeah, initial momentum equals final momentum equals 0. And that's just an easy way. It's a neater way to solve like a collision problem. Let's go to the center of mass frame. Does that make sense? All right. Final problem. This one should be this one shouldn't be too hard. The overall idea is just write your momentum conservation equation and then also write your energy conservation equation. After that, it's just algebra. And you'll get a very nice result, which will be theta equals to 90 degrees minus phi. Yeah, this is just a well-known result after you, and you'll find it after you solve the problem. Theta equals to 90 degrees minus phi. So again, just if you want to solve this problem, just do energy and momentum conservation, and you should be good. All right. We didn't spend too much time on the homework, which is good. So let's go on to oscillations now, which is one of the topics of our class today. All right. So first is the simple harmonic oscillation equation, right? This you might notice is for springs. So for example, if I have that's a wall, and then I have the ground over here, right? And I'll have I have a spring over here that's attached to the wall. Oh, let me draw that better. That's my spring, and then I have a block over here, right? Has mass m. Let's say the ground, the mu equals to 0, right? We're not going to talk about any friction. Then we have m and then x double dot, right? When I write x double dot, this is just the same thing as d squared x dt squared. It's just acceleration, right? Second derivative of the space of like position, right? So it's just a shorter way, a shorthand of writing it, right? So our F equals I beta equation is mx double dot equals to negative k, yeah, kx. If our spring has a non-zero rest length, let's say kx minus x0, right? But yeah, let's just keep it like that. Or for now, we can just say we'll find that it doesn't really matter because it's not really changing if x changes. So the simplest form would just be mx double dot equals negative kx, where our initial rest length is 0, right? If we want to solve this differential equation, let's first move over m to the other side. So I'll erase this one, and then instead, all right, on the right-hand side, I'll write negative k over m times x, right? And then how do I solve this? Well, notice that if I have x equals to, let's say, a times some amplitude a times cosine, so cosine of square root of k over m times x, or no, times t, right? if I plug x equals this into my equation over here, what do I get? Well, x double dot, hold on, x double dot, what was that? Well, I'm just taking the derivative twice, right? So if I take the derivative once, how about, yeah, let's first take the first time derivative, x dot that equals to a square root k over m. It should be negative because I'm taking the derivative of cosine, right? So it should be a negative a square root k over m times sine square root k over m t, right? And then if I do the second derivative, so say x double dot, I'm taking the derivative of this again, right? Then I'll be getting negative a again, except because I have a square root k over m inside, right? So it'll be a negative a times k over m and times cosine square root k over mt. And look at that. That equals to negative k over m times x, right? So that means that this solution to, or like this equation for x, that satisfies our differential equation for like the f equals ma differential equation, right? So this should be our solution. Of course, you might ask, oh shoot, sorry. You might be asking, for example, uh, like we can also have something like a cosine square root k over m t, and then plus some arbitrary like initial phase angle, they call it phi zero, right? And yeah, that is true. This is the most general form of our solution to the differential equation. If you guys know a bit more about differential equations, you'll know something about like number of degrees of freedom. So here we have 2 degrees of freedom, which is like we can choose an arbitrary scaling constant, which will be our initial amplitude. And then we'll also have an arbitrary like initial phase angle. And how do we determine these two numbers? Well, we'll determine them using the initial conditions. For example, if I give you that at time equals 0, this length is equal to L0, and my velocity is equal to 0. Well, first, if my velocity is equal to 0, right? So this should equal to 0. And then I also have that the initial, so x at time equals 0 is equal to L0. Well, if I just plug in t equals 0, then I'll get x0 is equal to a, which is equal to L0. And also I have that x dot in the beginning is equal to 0, and x dot is equal to 0. Uh that means that our phi zero is equal to 0, because once you take the derivative, you'll find that we're getting like we need to have phi zero to equal to 0, or yeah, phi zero has to be equal to 0 for us to have for it to satisfy these two initial conditions. So our final solution for that particular for those particular initial conditions, our final solution should be x as a function of time will be equal to L0 times cosine square root k over m on t. All right, that's our final solution. Now you might be wondering, what's the square root k over m, right? You guys probably seen that before. We've seen it's the omega of, they call it the angular velocity or the angular frequency of the simple harmonic motion. And there's a nice way to visualize this, okay? So for example, if I let me try to erase everything so that you guys can get a better picture. Maybe erase over here. Oh, so um yeah, we want to visualize our solution in a better way. So let me erase this first and I'll rewrite it for you guys. Uh, yeah. So remember our solution was, oh, so let's say was xt is equal to L0 times cosine omega t, where omega equals the square root k over m. What's the motivation for defining like an angular velocity? Well, the motivation is that if we imagine xt as a rotating complex vector, so instead of writing xt equals to L0 cosine omega t, I'd say xt, and this time I'll put it like a curly line over the x to like represent that it's a complex number. So I'll say it's equal to e to the I omega t, and then times L0, right? Because it has amplitude L0. If I imagine this on the complex plane, right? So I'll draw a circle over here in the complex plane. Okay, that's my origin center. And then notice that if this circle it has radius L0, then if I have xt, this is my complex number, it's rotating with an angular velocity of omega. Why? It's because when t equals to 2 pi over omega has made a full circle, right? So the period, that's equal to the period. And you know that period equals 2 pi over the omega. And clearly here, we also have omega, right? So the omega, or the angular velocity of this rotating complex number, is equal to square root k over m. That's the motivation for calling it an angular frequency. And physically, what does this mean? It means that basically there will be square root k over m number of these full oscillations every second. So a full oscillation is like where it starts, for example, it starts over here, and then it will travel, like maybe a spring will compress and it'll go over here, and then later it will go back to this position over here. That amount of time is the period, and if I do 2 pi over that period, I'll get the angular velocity or the angular frequency. So that's basically a nice way to visualize the solution to your simple harmonic oscillation equation. It's just to write it instead as a complex number and then visualize it on the complex plane. And that's just an interesting fact. You guys don't have to use that when you're doing actual problem solving. It's just a good idea. Or it's just an interesting idea, I guess. Yeah, any questions about that? Okay. Well, then let's go on to our pendulum. What is the differential equation to solve for the simple pendulum's motion? So what do I mean by simple pendulum? Means that I have like my ceiling there, and then I have a massless string, and at the end of the string, I have attached mass, right? I have mass m, and then we're saying that this angle over here, this angle theta is pretty small, so it's much less than one. Usually we say it's like less than, I think it's like 20 degrees, something like that. Uh, Basically we're assuming that theta is a small angle, so that sine theta is around theta. Okay. And under these conditions, let's set up the differential equation to solve for its motion. Does anyone want to step up and give it a shot? Here's a hint. It won't be an F equals ma equation. It will be a torque equals to your moment of inertia times your angular acceleration. So basically, we're trying to solve for the angle theta as a function of time. We want to solve for theta t. Anyone want to give it a shot? You're welcome to set like unmute or like type it in the chat. I'll give you guys like 30 seconds. All right, I guess not. So I'll just do the derivation for you guys. But yeah, I know you guys probably definitely know, or you guys definitely know that like, oh, someone has it. All right, Sudi, let's see. Take torque about the pivot point. Good. Mg sine theta equals, yeah, mg sine theta L theta double dot. Okay, nice, nice, nice. So yeah, basically what Sudi is saying is that we want to write the torque equals I alpha equation. So if the torque equals I alpha, we'll go over the derivation actually later in class of, or like I'll go over this idea of torque and moment of inertia later in this class. But now let's set up the differential equation. So we have our mass over here. These forces, there's going to be the gravity force down, right? And there's a tension force that points along the string. Now, if we take the torque at this point over here, it's a stationary point, and also this tension force over here, we don't need to worry about it when we're looking at the torque about this pivot point because the that tension force does not produce a torque. The force is parallel to the radius. The only torque is due to a component of this gravity force, right? It's pointing tangentially. So we have our torque, right? Our torque would just be due to gravity mg sine theta times the length of the pendulum, right? So times L, that equals to the moment of inertia times angular acceleration. What's the moment of inertia? Well, here, it's only the mass that has, or the mass at the end of the string. It's the only thing that has mass because the string we're assuming it's mass. So you can say this is equal to m L squared. So that's going to be the moment of inertia, and then times the angular acceleration. And that's just theta double dot. So the second derivative of of the angle with respect to time, right? By the way, this is actually a negative torque because this force over here it's creating a torque that decreases the thing, right? If you see it, right? Like the pendulum and once the string it swings or it's accelerating inwards, right? It's accelerating in a way so that your theta double dot should be negative. Your angular acceleration is always negative. So if we have this differential equation over here, then we cancel out the m's, this one cancels, and because we're assuming it's a small oscillation, we can say instead of saying sine theta, we can just write it as theta, right? That's a small angle approximation. So our differential equation is just, if I move this over here, then I'll get theta double dot equals to negative g over L times sine, uh, oh yeah, we said it was small oscillation, right? So it's just theta dot double dot equals negative g over L times theta. And if you notice that our solution will just be theta as a function of time is equal to the initial angle theta, theta zero, and cosine of omega t, where I'll let omega equals the square root of g over L, omega t, and then plus some arbitrary constant, like initial phase angle phi zero, right? That's our solution for the theta. And you definitely have seen omega equals square root g over L before. It's pretty well known. So this is basically how you derive. Um, Another result is the period, right? So period would just be equal to 2 pi over omega is 2 pi square root of L over G, right? So yeah, that's just the solving the differential equation for the pendulum's motion. It's just like it looks like identical to the spring differential equation. Because remember, in the spring, like in a regular simple harmonic oscillation for a massless spring, we had in that case we had x double dot, sorry, yeah, x double dot is equal to negative k over m times x. here we have theta double dot equals negative g over L times theta. So it's a very similar differential equation. This also counts as a simple harmonic oscillation because we can write our solution for theta as like a cosine or it's basically sine, right? Cosine or sine, any of that works, but it's like in the same family of solutions. Any questions about that? Wait, let's keep going.
So do oscillations generally take that form?
Uh, yeah, so simple harmonic oscillations. If we say it's a simple harmonic oscillation, just say it's like the solution is you can write it as like a cosine or a sine function, right? But not all oscillations can be written in that simple form. Like not all oscillations will have like the solution will be cosine or sine. There are complicated oscillations that exist, except you can't write it in that simple form. So we don't call those simple harmonic oscillations. We usually just call them oscillations or harmonic oscillations. Does that make sense?
Yeah.
All right, cool. Okay, let's keep going. Here's yeah, here's a problem. Uh, is the average over time tension in the string of a pendulum larger or smaller than mg by how much? As usual, assume that the angular amplitude A is small. All right, I'll let you guys do the problem. I'll just be drawing a diagram while you guys are doing it. So yeah, take like a few minutes. Let's discuss it at 35, maybe. Yeah. If you have an answer, oh yeah, if you have an answer, send me in the chat. Oh wait, let's talk about this problem. Okay, so we want to find the tension in a string, right? So, recall we can decompose the forces. So we have mg cosine theta in the radial direction and mg sine theta in the tangential direction, right? Now, um, so we already have our result that theta as a function of time, right? That would equal to like given amplitude A, right? So A times cosine omega t, right? Omega squared g over L. We'll assume that our arbitrary phase angle phi is equal to 0. Okay. So we're getting, oh wait, someone has an answer for us. Oh, Sid, do you want to talk us through your solution for how you got your answer? But I guess not, but okay. So all right, I'll just solve this problem then. Then okay, we have that this is our expression for theta as a function of time, right? Now uh we want to find what's tension, right? Well, you know we can relate tension to the centripetal acceleration. So T minus, or hold on. So I need enough centripetal acceleration so that we can have, so that like we can have circular motion, right? Because in circular motion, you need enough centripetal acceleration. Otherwise, the mass is going to fly off, right? So the radial direction of force will be T minus mg cosine theta, right? That must equal to m central acceleration. So m omega squared r, which is m theta dot squared times r. Okay, well, then our tension should equal to tension equals to mg cosine theta plus m theta dot squared r. Well, what's m theta dot squared r? We already have theta, so we can find theta dot. So theta dot as a function of time, that should equal to a omega or negative a omega sine omega t, right? That's just taking the derivative. So if we add m theta dot squared times r, or here it will be L, right? L, the radius of circular motion is the length of it's the length of the pendulum. So we'll get plus uh m times a squared omega squared sine squared omega t. All right. Now, all right, we want to take the time average of this over time. But first, we need to do something with this cosine theta, okay? Because we're looking at whether it's larger or smaller than the mg. Well, we need to use some small angle approximation of the cosine theta, okay? Well, remember for a small angle, cosine theta, that's around 1 minus theta squared over 2. So if I plug that in, then I'm getting T equals to mg. So mg comes from multiplying the 1 with the mg, right? Then we also have the second order term, right? What's the second order term? It will be plus hold on. So minus mg theta squared over 2. Oh wait, theta as the function of time, we already have that, right? It's right here. So instead of writing theta, I'll write theta squared, which we already know, which should be mg a squared cosine squared omega t. Okay, minus mg a squared cosine squared omega t over 2, and then plus this term over here, right? We didn't add that yet. So m a squared omega squared sine squared omega t. All right. Now what do we do from here? Well, hold on. Yeah, this is looking correct, I think. now we want to find the average tension. How do we find the average tension? Well, to find the average tension, we need to do an integral over a period of time, and then we divide by the total period of time. So if you guys don't know, if you have a function f and a function ft, right? If I want the average of f, and wait, let me make this clear first. If you have function f of t and it's periodic with a time with a period t, right? Then the average function, then the average of f, that would equal to integral ft dt, okay, from 0 to period divided by total period, right? If I do this here with my tension, I treat it as a function of time, right? Then wait, let me do the integral now. So first, of course, once you're doing the integral of mg and then over a certain amount of time, and then you divide by that same amount of time, you're still getting mg, right? So average tension, I'll write it as tension average. So tension with a like with that line on the top. I think that's yeah, that's the usual notation. That would equal to mg and then plus I need to integrate now, right? So if I integrate m a squared omega squared sine squared omega t, it's getting a bit messy. Sine squared omega t, um and then this goes from 0 to the period and divide by the period, right? And then minus the integral again from 0 to t of mg a squared cosine squared omega t, and then divided by 2t, right? Because I have a 2 on the denominator, but we're running out of space here, so yeah, I have to, how about, give me a second. All right, I might screw that. Yeah, how about ignore this text over here right now, and then I'm just gonna write on this slide, okay? So let's ignore this over here, and then so let's use what we got previously, right? We have this, I'll copy it over. So average tension, T average should equal to mg plus, right? Notice our period is t, it's 2 pi over omega, right? So integral from 0 to 2 pi over omega of, what was it again? M a squared omega squared sine squared omega t, okay? M a squared omega squared sine squared omega t. And then we divide by the total period, right? So this should be divided by 2 pi over omega. And then we subtract by, yeah, mg a squared cosine squared omega t. So this integral over here. Uh, yeah, over 2. All right, it's getting a bit tedious, not gonna lie. So let's try to get this quickly done. Uh, we need to look at these two integrals over here. Well, remember, if we're integrating, if you guys don't know, if you're doing integral of sine, for example, sine squared theta, right? And then d theta, well, what we can do is remember that cosine of 2 theta is equal to 1 minus 2 sine squared of theta, means that sine squared theta is equal to, let's see, it's equal to 1 minus cosine 2 theta over 2. So I'm doing integral of sine squared theta d theta, it equals to integral of 1 minus cosine 2 theta over 2. And now if my integration boundaries go from, this should be there, yeah. My integration boundaries are from 0 to the period, right? Because I know that integrating this cosine 2 theta, that'll turn into a sine, right? And then at the two boundaries, you'll find that they both evaluate to 0. So the result of this is just p over 2, right? Now I want to plug this in. Like basically, this is our result, okay? And if you do the same thing for the integral of cosine squared, so cosine squared theta e theta, that equals to it should be 1 plus cosine 2 theta over 2. That integral from 0 to t. So these are all the boundaries are all from 0 to t, okay? From 0 to t. Then this would also equal to t over 2 because this component, once you integrate that and take that as the boundaries, it will just go to 0. The only part that matters is this 1/2 over here. Now I'll erase all this because it's just a result from the integral, so that's better. Oh, wait, there should be 2 times 2 pi over here. Okay, now I know that out of these integrals, there's a bit of a complication there with the omega. That's fine. By the way, we should have a dt there. This is a constant. This is also a constant, right? So the result could be mg and then plus ma squared omega squared. Once I integrate sine squared omega t, I should be getting like, yeah, I'll be getting like 1/2 of the period, right? Because yeah, we got it's 1/2 of the period. So it'd be this over 2, and then plus mg a squared divided by 2. Um divided by 2 but times 2 pi over omega, right? And this should be yeah, the 2 pi over omega cancels. Mg a squared over 2. That's interesting. The dimensions are not correct. Let me see, we might have done something wrong. Hold on. So over here we had mg a squared. Oh yeah, I forgot there should be a square over here. It should be mg m a squared omega squared. So let's go back here. The a squared m. Oh, I did copy that over. Hold on. So our dimensions here, we both have a mass. We also have amplitude squared. So it's only omega squared and a g. So we are missing a meters term over here. Let me see what's wrong, guys. Let's see. Okay. First look correct. mg cosine theta and cosine theta minus theta squared over 2 a squared. Oh, uh, mg. Oh, okay, guys, this is just taking a lot of time. Let me see. There's a question. Why do you need to use integrals to find average tension? Can't you just use the known average values of sine squared and cosine squared instead? Well, yeah, it's the same thing. I'm just finding the integral. I'm just finding the integral of sine squared and cosine squared to show like what is the average value of sine squared and cosine squared because not everyone has the average value memorized. So, yeah, you could have it memorized and you would know it, but this is more than or this allows you to like see the reasoning behind it, okay? Yeah, I think we might have made a small mistake, but anyways, um, we can first answer the first question, okay? Whether the average tension is larger or smaller than mg, okay? Well, you can see over here, now we have mg, and then plus these two terms, right? Those two terms, um, oh, right. Give me a second. Yes, yes, yes. Yeah, I think there's an issue. Yeah. I think I've resolved the issue now. So there should be mg over there. I think we forgot to put that. So we should have plus mg, a squared, omega squared, and then hold up. Yeah, there was a minus sign over here. I forgot to copy it over. Yeah, it's minus over here. So this should be a minus, right? So yeah, we had it over 2 over here, so it just goes to mg a squared omega squared over 4. So our final answer, I believe, should be equal to mg plus mg a squared omega squared over 4. That dimensions still aren't correct, but I think it's fine. Like we can see, like basically we don't need to look at the second question, okay? Second question, that's just a bunch of math. The first question overall, you can see that the average tension that's equal to mg and then plus a term on the right. The term on the right, that's greater than zero, of course, right? So you can get that the average tension in the string is greater than mg. Yeah.
Yeah, I have a question.
Yeah, what's up?
Is it possible to do like, is it possible to do this problem using energy methods? At least the conceptual part.
Good question. Well, the problem is, right? We want to look at the tension here, right? The thing is,
Yeah.
if we want to use energy, right? I'm assuming we want to find like work done by tension, something like that, right?
No, I mean like combine the fact that tension has to provide the centripetal force with energy to find the speed,
Yeah,
which it's yeah.
yeah. The problem with that is that like tension here, if we want to relate tension to energy, it's pretty hard because first off, like the string here, right? It's you can't really think of it as a spring. So because like I think what you're thinking of is like in the spring, if we know the tension, then you can get like the last potential energy. The problem is we're looking at a spring here. So just because it has tension, it doesn't really have any potential energy. Also like I see what you're trying to think of. Like we're trying to relate tension to energy, but if we want to look at, for example, work done by tension, notice that the tension is always pointing radial, right? But your mass is traveling in the tangential direction, so the tension force doesn't do any work on the traveling mass. So it's really hard here to like relate tension to any like work done because if we know the work done by tension, we can do like change in energy, right? And if we know change in energy, then we can go back and find the tension force, right? Problem is here, the only force that's doing work is the gravitational force. Your tension isn't really involved in any like energy exchange in this problem. But if we had a different problem where tension was doing work, like for example, if you had maybe some complicated system where you had like a rope over here and then you have a mass over here and the mass is moving, then yeah, using energy methods to solve for the tension, that's a potentially possible way to solve the problem. But unfortunately here we can't really use tension. Does that make sense?
Well, I mean, kind of, but like my point was that we don't just use energy, we use the fact that tension has to provide the centripetal force, and we combine that with the fact that we know whatever the speed is of the like ball using energy and with the gravitational force, and then so we know that we know our mv squared over r. That was my point.
I see your point. Okay. I get. Um yeah. I think I know what you're saying because we have that's a very good point. So I think what you're saying is like we have our we have a pendulum here, and then like we know the energy is conserved, so if we can find the change in height, right? So if we know delta H, and then we get when the pendulum is maybe when the pendulum is over here, then we can say like we can
Yeah,
say
we can
this
find its speed and
yeah,
then
point. Yeah. Um, yeah, that's actually a good idea to solve the problem. That's another way I think you can get the differential equation for the data as a function of time, like basically using energy conservation. That is another way. Other like you can do this method instead of writing your torque equation. Uh yeah, this is an alternative route. Like what this will get you is that you'll get your theta as a function of time. And again, when we do that, once we have theta t, then we can say centripetal acceleration equals to mg cosine t minus mg cosine theta. Yeah, this works. It's just a bit messy when you're trying to find the change in height because you'll have to work with like infinitesimal and you'll have to do some geometry. But I see where you're going at. Like this does work, I think. Yeah, good
okay.
idea. Yeah. Um, yeah, let's keep going. Um, let's talk about this one. Show for any general oscillation, not necessarily simple harmonic, about a point where there's forced equilibrium, the angular frequency of the oscillation can be written as omega equals square root of the second derivative of the potential energy about the equilibrium point divided by the mass. You guys, maybe a minute to think about this. Yeah, so the overall idea about this is like okay, if I want to write my potential energy, I can write it as a Taylor expansion about the equilibrium point. So if I write a Taylor expansion about R0, then I have U R actually equal to um that'll be equal to U R0, right? And then my Taylor expansion is plus U prime R0 times like R minus R0, and then plus like U double prime R0. By the way, double prime just means I'm taking the second derivative with respect to R, right? U double prime R0 times R minus R0 squared over 2, and then plus like U triple prime R0 R minus R0 Q over 6, right? And then so on, right? It goes to infinity, right? Now, what am I looking at here? We're looking at a general oscillation. Remember, it's not necessarily simple harmonic about a point where there is forced equilibrium. We want, it's a small oscillation, okay? So that means R minus R0, we can treat it as an infinitesimal. We can treat it as something that's very small. And also, there's forced equilibrium. So that means that U prime R0, because it's U prime at R0, it gets you the force at R0. So this is just the force. Well, we're given its force equilibrium at R0, so this just equals to 0, right? This is just an arbitrary scaling constant. And then if we just look at this second order term over here, Okay, focus on the second order term. We can neglect these terms after the second order. The reason is because r minus r0 is an infinitesimal. So this term over here, that's going to be infinitesimally smaller than this term over here. Now, if we're looking at the second order term here, right? U double prime r0 times r minus r0 squared over 2, doesn't that look oddly familiar to if you have UR for a spring, that equals to K times R minus R0 squared over 2. And in that case, we have our omega was square root of K over M, right? It looks pretty familiar to me, right? It should, right? And then if we're only looking at the second order term, in other words, we're approximating oscillation as roughly simple harmonic. Remember, I'm saying it's a general oscillation, except around the equilibrium point, if my displacement is very, very small, then I can approximate it as a simple harmonic oscillation. Then I can treat it as if it's sort of like a spring, right? That spring constant U double prime R0. So then my omega would just be U double prime R0 over M. It's just like it's square root K over M. It just looks like it's square root K over M. It's basically, we're just approximating it as a simple harmonic oscillation when there's a very, very small oscillation about the equilibrium point. So the condition for this to hold, basically, you need to have like some oscillatory behavior, and you need to be looking at an oscillation about a point where there's force equilibrium, because that allowed us to cancel this U prime term over here. And because it's a very small oscillation, we also neglected those higher order terms because those are infinitesimal. And we can also just neglect this because it's just a random constant you add to the potential energy. Potential energy, that remember, like you can add any arbitrary constant to potential energy, it won't really change it that much. So yeah, this identity over here is really helpful. Like omega equals square root U double prime R0 over M. It's really helpful and it works for any oscillation. Does that make sense? Okay. This one I'll give it to you guys for homework. It's just working out the math. The overall idea. Let me see. Wait, there's a question. Why do we neglect U prime and prime? Good question. So, so the picture is first U prime over here. Remember, we have a potential energy. Let me give you guys more space. So, there we define. Okay, how about I'll work over here so that we have a bit more space. To answer your question, remember, U prime. Oh shoot, U prime. What is that equal to? Well, remember we had U, we said it was in a negative integral of F dot, like force dot displacement, right? So that means that the derivative of U, that just equals to negative force, right? Now, if we go back to over here, here I have the derivative of U, right? So U derivative is equal to negative force. But I'm given as a condition that we're oscillating about a point that has force equilibrium. So the force is equal to 0. So U prime is just equal to 0. So we can neglect that U prime term. Now, as for the U triple prime terms, because we're looking at a small oscillation, so I'm saying that R minus R0, so R minus R0, that's infinitesimal. So if I look at the R minus R0 cube term, how about I draw here? So R minus R0 cube would be infinitesimal compared to the R minus R0. And so would be like R minus R0 to the fourth power and so on. So because those terms over here, these are basically just 0, then I can neglect the third order term and higher. And I can also neglect the first order term because there's force balance. So we're just left with the second order term, which is just the potential energy of the spring. See, there's, oh, got it. Yeah, right. Yeah, good. Yeah, no problem. Uh, yeah, let's keep going. This one, by the way, is just doing the math. You just need to do u double prime, square root of u double prime divided by the mass. There's a small nuance over here that we're looking at two atoms. But I'll let you guys figure it out in the homework, or I'll send an email to you guys. But first, let's talk about rotations. This is our second part of the class. Here are a few definitions. We're talking about 2D rotations, by the way. So a lot of things are different in 3D rotations. You'll find that the moment of inertia is the tensor, angular momentum is much more complicated. Here, let's first look at two-dimensional rotations. It will be much simpler than three-dimensional rotations. So in 2D, this is our angular momentum. If we have a system of just like distinct particles, we can write it as a summation of like r plus p, right? But if we have like an object, for example, I have this object over here and it's rotating, then I'll have to do an integral because I can't, well, I mean, it's the same thing as summing up over each like infinitesimal small mass. Formally, you write it as an integral, right? Now, this is my integral of r plus p, and I'm assuming that this mass over here is like rotating about center of mass. So it's rotating about a center of mass, and its velocity will be omega cross r. Of course, some people read it as r cross omega. It's the same thing. Just be aware of what you define as your r. I think we went over it on the first class, but like just use your intuition to find out whether it's r cross omega or omega cross r. But it will be, this is your integral, right? So r cross omega cross r times df. Now we're talking about a 2D rotation here. So if it's a 2D rotation, we're saying that this is my object over here. It's basically think of it as like a pancake. It's like a flat object. It doesn't have any like extensions in 3 dimensions. It's just two-dimensional space. It's like a two-dimensional body, but it's in 3 dimensional space. And when it's rotating with an omega, it has to rotate in the same plane. So the omega, or not the omega, it will be rotating something like that. So it's rotating in its own plane. Then if it's rotating that way, then the angular velocity will be pointing out of the page. So pointing that way. Then because omega is always perpendicular to your r, because omega is in the perpendicular plane, your cross product, the magnitude of omega cross r, that's just equal to omega r, right? So our integral just becomes that, right? Erase myself. Yeah, that's our integral. It's the integral of r squared dm. And notice we can pull out the omega because every part of the body is rotating with the same angular velocity. And we get the definition of we get a definition of moment of inertia. So we're saying L equals to this integral times your angular velocity, and we're saying the integral over there, that's your moment of inertia. You might have seen it before, integral r squared dm, okay? Uh, yeah, that's your moment of inertia and your angular momentum. Now, yeah, this is just, yeah, velocity of a point on a rotating object that is vector r from the center of mass. It's your velocity would be the center of mass velocity plus the omega crosses the r. So basically, you superpose the velocity due to center of mass motion with the velocity due to rotation. For example, if we have a ball over here and it's rolling without slipping on the ground, right? And then I want to find the center of mass velocity. Well, if it's rolling without slipping, I'm saying that this point in contact with the ground, instantaneously, this velocity should equal to zero. How would that work? Well, if I'm looking at the velocity by looking at the center mass, or like basically using this equation over here to find the velocity over here, well, then this velocity here has to be equal to my VCM minus uh VCM minus omega plus R, which here will just be omega R because omega and R are perpendicular. This must be equal to zero, so we just get, of course, this should be obvious. VCM equals omega R. It's a pretty well-known result. I'm assuming you guys know it. This is the result for the center of mass velocity. Yeah, that was just an example, just to get you guys warmed up, right? And of course, we have torque over here. Torque equals force cross R, and it's also equal to the derivative of angular momentum. Is similar to F, sorry, similar to you have F equals to dt. Here we have torque equals to dl dt. And if you use, I omega, you put it in here because we're assuming that like the mass distribution of the object, it's not changing. So we're saying that torque is equal to the moment of inertia times the angular acceleration. Those are just some definitions. Any questions about that? All right, I guess not. So let's keep going. Some common moment of inertia. Well, for example, if we have a ring over here, sorry, we have a circular ring, right? Circular ring, it has radius r and it has total mass m. Well, of course, when I'm doing integral of r squared dm, I'm just getting mr squared, of course. Now, if I instead have I have a disk, okay? I have a disk, it's not a ring. Then if I'm doing integral of r squared dm, notice that this over here, it's the same as adding, wait, hold on. Right, it's the same as adding up like the moment of inertia of a bunch of small rings. So basically, yeah, I'm basically adding up the moment of inertia of a bunch of rings over here, right? Now, it's a bit more complicated than just doing the integral of mr squared. Of course, every ring would have a different mass. Smaller rings would have a different mass. The smaller rings will have a smaller mass than the bigger rings, right? So let's say that, let's be a bit more rigorous, right? Let's get this ring over here. Say it has a mass density of sigma. Then if I integrate in my rings, right? So it will be integral of basically, for example, if I'm looking at this ring over here, it's a radius, let's say I'll use B, it's B away from the center. Then the total mass would be 2 pi B and then times dB, because that will give us an area, right? We're looking at a ring with infinitesimal thickness, and then 2 pi b dB times sigma, and then times b squared, because it will be the distance from the center. Then I integrate from 0 to the radius, right? What's the result of our integral? The result of our integral, well, yeah, yeah, this looks correct. So we have 3 powers of b here, right? So it's 2 pi times b4 over 4 times sigma, and we plug in 0 and r, right? Those are our boundaries, and of course, 0, 1 cancels out. So instead of writing b, we have, all right, 2 pi r4 sigma over 4. So it's just divided by 2 here. And because we have 2 pi, oh, sorry, pi r squared sigma equals to mass, so we have m r squared over 2 equals to the moment of inertia of a ring, right? So that's basically how you get the moment of inertia of a ring. You can get moment of inertia of the stick by doing a similar thing. You're just doing the integral of the dm r squared. Yeah, that's the overall idea. Parallel and perpendicular axis theorems. You guys might be familiar with this, but if we want to find the moment of inertia of an object about an axis r from the center of mass, we have this, which is moment of inertia. Let's say, for example, I have this body over here. Body over here, this is my center of mass, let's call it G. And then I'm looking at an axis, maybe it's going, say that's my axis, right? Then I have another axis that's like, it's over here, right? then if that's my center, G is my center of mass, by the way. So if this distance is R, then the moment of inertia about this axis over here. So let's draw it in green. This green axis, moment of inertia about that axis would just be moment of inertia about the center of mass plus the mass of the object times this distance squared. There is a proof of this. It's not that hard. You guys will probably understand it, but this is just statement of the parallel axis theorem. Pretty useful. A bit less useful theorem, but it still can be pretty useful. If you have a pancake object, we say that's the xy plane, right? So it's a flat object. Then we're saying Ix equals to integral y squared dm, Iy equals integral x squared dm. Might be wondering, why do we have the, like, for example, Ixy are we integrating y squared and not x squared? Well, the reason is because, remember, we're saying moment of inertia, we're doing the integral of r squared dm, where r is the distance from the, like, the infinitesimal mass we're looking at, the distance from that infinitesimal mass to the axis. So if I have a pancake object, let's say it's a flat square, right? And this is my center mass, it's at the center. Then if these are my axes, right? So I have x direction and y direction. Well, if I'm looking at a point on the x-axis, the distance to the x-axis would be 0, right? But the distance to the y-axis would be x, right? Or like whatever the x coordinate is. So I'm not integrating the x coordinate when I'm finding the moment of inertia in x direction. I'm looking at the y-axis. Sorry, I'm looking at the distance to the y-axis. So it would be Ix equals integral y squared dm, Iy equals integral x squared dm. Then Iz, which is yeah, Iz would be like I'm looking at each mass and its distance to the z axis. And because it's a pancake object, that distance squared is just x squared plus y squared, right? And because like we can add two integrals together and we can find them into one integral, Ic is just equal to Ix plus y. And that's a convenient result. That's just the axis theorem. And yeah, it's convenient sometimes, but I'd say the most useful one would be the parallel axis theorem. And it's also more well known, right? We're a bit out of time, so I'll just quickly go over a few ideas and I'll let you guys go. So here's a good idea. It is most convenient to calculate torque about the center of mass or a stationary point. The reason is so that we won't have to worry about torques produced by fictitious forces. What do I mean by that? Well, basically, when I'm looking at the torque about some point, it's equivalent to taking the frame of that point, and then I'm looking at the torques about that point, right? But I still want to, like, basically, if I say torque equals I alpha, this alpha is the angular acceleration about that point, right? Then if I want to find the angular acceleration of the object about that point, I need to take the frame of that point. Now, if that point I'm taking the torque about is the center of mass, then when I'm taking the center of mass frame, right? So for example, I have this object, it might be moving in this direction, it's also rotating, right? This is the center of mass. If I take the center of mass's frame, there would be a fictitious force on the center of mass in case the center of mass is not going through inertial motion. The center of mass is accelerating, right? There would be a fictitious force, and that fictitious force is applied to the center of mass. The thing is, we won't have to worry about the torque produced by that fictitious force because your R for that fictitious force is equal to 0. Your F is not equal to 0, but your R is equal to 0. So the torque produced by that fictitious force is equal to 0. But if I look at a point over here, say it has a non-zero velocity, but it's also like going through non-inertial motion, then there will be like there's this fork about the center of mass because I'm taking the frame at this point. Sorry, wait, what was I saying? There's a force that's applied at the center of mass because I'm taking a non-inertial frame. And because there's a force at the center of mass, there's a possibility that it creates torque about the point I'm taking the torque about. And when I'm doing that, that's going to be a problem because I need to calculate that fictitious force. And usually it's like a pretty messy calculation. it's most convenient if I either do torque about the center of mass, or I do torque about the stationary point, or equivalently, a point going through inertial motion. So this can also be a point going through inertial motion. And that's so that we don't have to worry about torques produced by fictitious forces. If you want to apply this idea, this problem, we won't do it now because we're out of time, but basically we have a cylinder that's rolling down a ramp. Uh, we want to, oh, sorry. Now we want to find the minimum coefficient of friction. Basically, the idea is you can take torques about 2 points. You can take torque about this point over here, which is in contact with the ramp, and it will be go like that point over there instantaneously. It has zero velocity, right? Because we're saying we want the cylinder to roll without slipping. If that point over there has instantaneously zero velocity, then that means that there will be no fictitious force once we take that point's frame, and we don't have to consider the torque produced by that fictitious force. We can also take the torque about this point in the center, which would be the center of mass, right? Because if we take the torque about center of mass, of course, the fictitious force will go through the center of mass, so there will be no torque produced by a center of mass. So yeah, basically find the minimum coefficient of friction. You take torques about 2 points, you equate the two angular accelerations, and you'll get your final answer. That's basically how you do the problem. I'll leave it to you guys for homework, but yeah, we're actually able to go through a lot of the stuff we want to cover. Remember, this is just kinetic energy of a rotating object. Proof will be for homework. But yeah, we got through all of the slides, which is a good thing. So yeah, so basically today we talked about oscillations, we talked about rotations. Um, Next week we'll be talking more about rotations, and then we'll also talk about gravitation, like Kepler's law, um, the elliptical, hyperbolic, and circular orbits, stuff like that. So have you guys enjoyed the homework for this week? And yeah, I'll see you guys next week. Thanks for coming.
Thank you.
Yeah, you're welcome.